Fundamental theorem of calculus, there's two parts to it. So we're going to do part 1 first, which is actually, I would say, less used. And part 2, you're going to see it today, and it's kind of the next lesson also. So part 2 you'll get really good at because you use it so often. Part 1 people kind of forget about sometimes, or don't use it when it makes problems way easier sometimes, and they make the problem way more difficult. So it's definitely something that's worth taking the time to really understand and not just be able to do it for your homework for a few problems. So fundamental theorem of calculus, part 1. If f is continuous, then the function g defined by this is continuous and differentiable, and this is the key right here. So I'm actually going to highlight that. So our g prime is equal to f of x. So we move from this, from it being in an integral, to it just being the derivative. And I know it doesn't make sense right now, but we'll just do one right here. So if I take this here, this is what it starts out as. These are a lot of times free response questions, and it will look like this type of a thing right here. So you'll notice it because there'll be an x on the integral, and then it'll usually be in terms of t inside the integral, so you'll know it's one of these type of problems. So if the x is at the top, which it is, you just plug it into here. So if you plug x into there, don't you just get f of x? Okay, so this is just going to become f of x. And then that's equal to the derivative of this side. So when you plug that in, it's actually giving you the derivative. So that's what this says right up here. Do you see that? And we'll do some problems on the next page where there's actually functions inside there, but they're really easy to do. So this is more like the AP question. So evaluate g of x for all of these spots here. This we're going to use more for other problems or other parts of problems. That's always the first thing I write down because it's always the easiest thing to forget to utilize for these type of problems. For this first part here, it says evaluate g of x for 0. So let's say I plug 0 into g of x. Wouldn't I just be plugging 0 in here? So then my x would turn into 0 here. So if I'm trying to find g of 0, I'm really just taking the integral from 0 to 0. So what am I going to get? 0, right? So that's just 0. If I try to find g of 1, I'm plugging 1 in for that x. So instead of zeros there, we'll put 1s there. So it's going to go from 0 to 1 of the function. Let's just be a 1 up there. So then you're looking at this picture here. So this is f, the function that's shown. So we're trying to find what the function is from 0 to 1. So you guys did a lot of this in the last lessons. You guys use rectangles. Do I need to use a rectangle here? No, and it's not asking for an estimate. Okay, it says evaluate it. So there should be an exact answer. So if we're going from 0 to 1, what is the area of that? Half. So this is just 2.5 or 1/2 there. You're going to go ahead and find 2, 3, 4, 5, 6, and then for part B it says estimate g of 7. That's just because it's not linear back here. You're not going to use a rectangle. You're just going to try to estimate what that area is. So I'll give you guys a minute to get ahead there. Okay, are we getting some answers there? So when you did g of 2, I'm not going to write out all the 0 to 2 thing here, but if we're going from 0 to 2, what's going to happen to this area and this area? It's going to like cancel, right? Because the one's positive and one's negative, so we just get 0. Does that sound good? Okay, so then we move to 3. So it's kind of like we're starting over. So for 3, we're just looking at the area from here to here, which is what? Negative, right? So negative 1/2. At 4, then we're back to what? 0, because these will cancel each other out, just like they did before. So it's kind of like we're starting over again. So at 5, I mean, we're doing all of this, but the first 4 pieces cancel. So we're just looking from here to here for our new stuff. So that's what, 1.5 or 1.5. And then at 6, we're taking 1.5, and then we're adding 2.5, it looks like. So did you guys get 4? Okay, and then we're estimating what g of 7 is. So that's going to be taking g of 6, and we're going to add on the area from 6 to 7. Does that make sense? Okay, this is how the AP test, how they write a lot of their answers. It's not necessarily how you would have to write it. But when we get to studying for the AP test, a lot of people go, what does that even mean? It means you're taking what you had at g of 6, and then you're just adding on what it was from 6 to 7. So from 6 to 7, our function, that's the part that we're estimating. So from here to here, it looks like it's almost a full box there. I would say it's probably a little less than 2. What'd you guys put for that part? 1.8, that works. Let's put 1.8. So we end up with approximately 5.8. That look good? Now, part C and D, sometimes, sometimes it's fine to look at C and just do it there. With this, it's probably okay. Sometimes when you get stuck on something, it makes sense to try to jump to the next part, and sometimes that helps you answer it. When we're doing this sketching a rough graph, g of 0 is 0. That's the point 0, 0. So you just plot a point at 0, 0. When we get to 1, it's at a half. When we get to 2, it's back to 0. And do you see what I'm doing? I'm just plotting the points we had from above. 3 was negative a half. 4 is 0. So on there. 7 kind of goes off of there, so just sketch it above. So this is what that graph looks like. So sketch a rough graph. We actually want to fill it in here. Does that look about right? What you guys have? So our sketch is done, and then sometimes it's a little bit easier to answer the question that's right here. So where does G have a maximum? So we could say there's a local max here, but when it's asking a maximum, it's asking for absolute, so it'd be at 7. At x equals 7. And where does it have a minimum value? At 3, looks good. Questions on that? Now, that's kind of time consuming because sometimes they will just give you this and they won't ask you to find all of these values, and then they're asking you this question anyway. So just looking at the graph without having to with just more or less thinking about it. Okay, do you see how the area is very small here? And the area from here to here is more, and it's negative. It's going to have a minimum at that spot then. Does that make sense? Because here it's increasing. It's increasing for that much, so that's what this represents right here. It increases to a half, and then it's going to decrease by 1. So there's more negative than positive, so the value is going to be negative there. And then from here to here, the area is what? Positive. So if the area is positive, that means the function is going to be doing what? Increasing. So really from here to here, because the area is positive, the function is increasing. And then from here to here, because the area is negative, the function is decreasing. And then here the function is increasing again. And do you see how, okay, it increases from here to here, right? But do you see how much it's increasing from here to here? That area is so much bigger, so then you know the maximum is going to occur here. Okay, the two possibilities for where there's a maximum are this spot and this spot. But this one far outweighs the other one, right? Because that negative area was so small that it didn't decrease by very much, and then it increased by a large amount there, okay? So you can kind of answer some of those questions without maybe having to do all of the steps above. Okay, this a lot more, I think, straightforward than that one, but like I said, this is very much like a free response type of a question, and you might have to, do this stuff here too. Like that could definitely be like what the free response question is test. So here, use part 1 to find the derivative of the given function. So remember, I talked about it right here. If I just plug that x in, let me clean that up a little bit. If I just plug that x into the function and make that f of x instead of f of t, then it gives me the derivative. So the biggest thing that you need is you need that variable on the top. Is the variable on the top? Yeah. So I would maybe make yourself a note of that. X on the top, obviously here it's y, but you need the variable on the top. And if the variable's on the top, you just plug it in. So if we just plug that in, we get what? Y squared sine of y, right? You just plug that variable in for the variable that's in here. The dt, you don't need to worry about, right? And this number here means absolutely nothing for the fundamental theorem of calculus part 1. Okay, so it does not matter that that number changes from 2 to 2 to 1. That doesn't matter. And that's equivalent to what? G of y or what? The derivative. So g prime of y equals this. And isn't that all it was asking for was the derivative? Okay, so that's your answer there. So what do you think you have to do if the variable's on the bottom? Yeah, so we flip it. So when we flip the integral, the x goes on the top, the 2 goes on the bottom, and then when you flip it, if you remember, we have to put that negative out front. Everything else stays the same. And then if our x is on the top, we do what with it? Just plug it in. So that negative, you don't want to ignore it. So we've got negative, and it'll turn into cosine of x squared, and that's equivalent to f prime of x. Just use whatever letters they're giving you there. No, because it's finding the derivative. So if you think about like the plus c thing, that's when you take the antiderivative, right? But then we're taking the derivative of that, so then the plus c goes away, because if you take the derivative of the constant, it goes away. Does that make sense? It's kind of like you're taking the antiderivative and then taking the derivative. And if you do that, doesn't it make sense if you take a function and you do the antiderivative and then you do the derivative, you end up really like at the same spot? Okay, you just have to make sure that x is at the top. And this one here is a little bit more tricky, but it's not crazy amounts more tricky. Do you see how it's not just an x there? So first thing you want to do is get it to the top. So you guys know how to do that. So to get it to the top, you put the negative out front. And you've just got your function here. And then you just plug it in like we did on the previous problems there. So if we plug this in, we have to plug this in for the u's. So the negative's still up front. I'm just going to write it so I don't forget it. U cubed turns into this cubed. And you don't really have to clean it up typically. 1 plus u squared will be that squared. And then it's like the chain rule. So if it's not just x, you have to remember the chain rule. So what is the derivative of this? Negative 3. So then you have to multiply by negative 3. Or by whatever the derivative is. Okay? So then we take this and multiply by negative 3. And that's equivalent to the derivative, right? And we could clean that up a little. There's 2 negatives there, so you can make that positive. The 3 I would just put in the front on the top. Does that make sense? Questions on that at all? I mean, it's easy to forget about the chain rule there, but it's really easy to remember the chain rule too. The book describes it way more complex, and I used to try to teach it that way, and it was really, I don't know, kind of unclear. And if you just think of it as the chain rule, multiply by negative 3 or multiply by whatever the derivative is, it's really quick. And most of the time on the AP test, They're questions that are more like this, where you don't even have to use the chain rule, but just watch for that, because it definitely could happen. So that's part one. Part one's really easy overall, right? It's just easy to forget because we don't use it a ton, except for in this section and problems that are very much set up to use it. Part two, you use like all the time. So we're using it in 4.3 as part two of the fundamental theorem of calculus. It's also called the total change theorem, and that's what the next lesson is on. So we're going to use this like a lot. And this is kind of like when you do derivatives. You know, derivatives are like the whole first half of the class. Antiderivatives are like the whole second half, and this is the majority of what you do when you're doing an antiderivative. So do you guys remember how that one problem had limits on the top and bottom of the integral? And I said, oh, we don't know how to do that yet, but you'll learn. This is where we're learning that, okay? It's not difficult to evaluate with those on the top and bottom. The only thing you have to do is take the antiderivative first to get it out of the integral. So what is the antiderivative of x to the fifth? 1/6x to the 6th. And if you have limits, you don't put a plus c. And then you put this line back here, which is saying I'm going to evaluate it from -1 to 3. Okay, so antiderivative, and then you just put the line back here. It's saying I'm going to evaluate that from here to here. So if f is continuous on a to b, then it looks like this. What you do is you take the antiderivative, so that's the capital F. You plug the top one in first, and then you subtract, and you plug the bottom one in second. So we're going to go ahead and we're going to plug the top one in first. Instead of x, we have 3 to the 6th. And then we subtract, and we plug the bottom one in second. Does that make sense? And then just go ahead and evaluate that. If you want to use your calculator for it, you can. They wouldn't probably give you, a 3 to the 6th type of a problem without your calculator, although you could do it. This one I'll have you try without your calculator and just get your answer as a fraction. So I'll give you a minute to work on that. This one, no calc. And this one, no calc. And the first one you could have done without a calculator. Switch it to a fraction. What do you get for the first one when you get there? What are you getting? Okay, can you switch it to a fraction? You know how to do that in your calculator? Like that math button off to the side. 364 thirds, sounds good. Okay, so go ahead and try those other 3 there. If you need to work together, you sure can. And then we'll move to the last page once we feel good about those. Okay, so the third one is pretty easy. You guys didn't even flinch, did you? What did you get for that one? You started doing it? Yeah, it's one of those where you look at it and you go, oh, do I have to do a U substitution? And then you go, oh, I'm going from 3 to 3. So if you're covering no area, you don't even have to worry about it. This one here, a lot of times people rewrite it. So I'll just do that. I don't know if you guys have to or not. Yeah, I was going to say I have to, otherwise I feel like I'm going to mess it up. So the 3 just stays out front. And then t to the -4th, when you add 1 to it, it becomes t to the -3rd, and then you divide by -3, so something like that, right? And then you're still going to be going from 1 to 2, so I'm going to write it, but I'm going to clean it up before I plug in. So this just turns into -1 over t cubed. Is that what you guys wrote, right? And then you just have to be careful with the positive and negative because of the negative already being there. So you plug 2 in, you get -1 over 8, 2 cubed. And then you're subtracting -1 over 1. So you're actually adding that. So this is 8/8 minus 1/8. Do you guys get 7/8? Good. Questions at all? Okay, and here it's just a matter of knowing the basics of the unit circle in order to do it without your calculator, which they do expect you know the unit circle. The antiderivative of sine is negative cosine. And then you're going from pi over 4 up to pi over 3. So you plug in pi over 3 first. And then you're subtracting the negative, so adding the cosine of pi over 4. Okay, pi over 4 I think is easier. What is pi over 4? Square root of 2 over 2. And the cosine of pi over 3 is you get a half. That is right. Or you're not sure and you just kind of guess? Yeah, a little bit. Okay. So if we're doing that, let me see if I can find a, because you're going to have to be able to figure it out, you know. Yeah, so let's just look at it again. It's good to review these things as they come up. Okay, so we've got 0 here. This is obviously pi over 2, right? And I'm not even sure if pi over 4 is on this one. Here it is, right? Some of them have it, some don't. So this one here is one of them, and this one here is the other one. So which one's smaller? Pi over 6, right? Because it's 1/6, where pi over 3 is 1/3. So this is 1/3 from here to here. So knowing where the spots are is the first thing that you need to make sure you know. And then knowing the spots, there's different ways that people memorize this, so I'll just kind of point them out, and then you can go, oh yeah, that's how I remember it. When you write these coordinates, a lot of times people think 1, 2, 3. So this one's a half, and then square root of 2 over 2, and then square root of 3 over 2. So they look at it like that, and then this one stays the same, you know that, right? And then these ones just switch. Oh yeah, so that's why I went with a half. Yeah, it's important to know that those are, you know, kind of your 3 possibilities. These ones happen at the halfway mark, and these ones just obviously flip. But those 2 you need to know. So sometimes people just remember it because it's, you know, 1, 2, 3. So you're thinking of it that way. Which comes first, sine or cosine? Cosine. So it goes cosine of theta and then sine of theta. So if you're trying to find cosine of pi over 3, you're looking at 1/2 there. You see that? The other way you can think of it is you have like a triangle from here to, you know, wherever on there. And if you think about that triangle, the length here and the length here represent this x and y coordinate, right? They both have the same denominator. Which numerator is bigger, 1 or square root of 3? Square root of 3, right? So do you see how the height is bigger here? So it makes sense that the y value would be the larger one at this spot. Okay, and if you move here, it's the same idea, but your x value is longer, so then you know the bigger number has to be your x there. There's definitely a lot of different ways to think about it. You just have to be able to, like, come up with those in a quick manner, and obviously be accurate about it. If you just have them memorized, that's great, but I'm terrible at memorizing things. The 1, 2, 3 thing is what helps me the most, I think, so. Yeah. Yeah, on the other side it goes, yeah, 1, 2, 3, and then 1, 2, 3 back. And this point up here, if you're thinking coordinates, it's 0, comma, whatever, right? And it always goes cosine first, so 0, 1 on a unit circle. And this one here would be the 1, 0. And then you know symmetry will get you any of these ones, right? So you can find those spots, yeah. Yep, so like over here, the x's or the cosines would be negative. Down here, sines and cosines are both negative. And then here, the cosines are what? Positive, and the sines are negative. Okay? All right, let's go to the next page here. Okay, this one, a lot of people still will use like U substitutions. So I'm going to, again, show you the shortcut just because, especially if you're going to take AP Calc BC or do more calculus in college, it really shortens problems up. So if you have a linear function in the denominator, you can't do what we did on the last page where you say, oh, it's x to the negative first, and then do the antiderivative, because what happens when you add 1 to that? It's 0 and it goes away, and then you don't really have a function anymore. So what is it if it's linear in the denominator? Natural log. Okay, so you have to use the natural log. So we do natural log of the absolute value of the linear function. And then who remembers what we put up front? No, that's okay. So think about taking the derivative of this. If you take the derivative of natural log, isn't it 1 over that? Which is what we have there, but then you have to multiply by the derivative of the inside, which is 2. So what would I need to get rid of that 2? A half out front, right? Do you see how that would get rid of that piece? So you always do 1 over the slope out front. So let's just write that here again. If we've got 1 over, I'm just going to write it as mx plus b, so 1 over a line. Then the integral of that is natural log of the absolute value of mx plus b, and then what goes out front? I didn't really leave myself enough room. 1 over what? Yep. And that keeps you from having to do a u substitution, because having to do a u substitution really slows you down on problems like that, and they happen all the time in integrals in Calc 1 and Calc 2, so it's just worth figuring that part out. Okay, so then we're going to evaluate this from 1 to 9, so that part you can start there. Is everyone okay with this? Half natural log of 18 minus half natural log of 2. And then a lot of times they try to combine those, so this is the laws of logarithms, which you know, but maybe you're not sure that you're going to do them right. So I'm going to pull a half out of everything. And what do I do if I'm subtracting 2 logs? So subtracting, how can I combine those logs together? Nope. Divide. So this would turn into the natural log of 18 over 2. Okay, you just divide those, so it actually is the natural log of 9. And then what can you do if there's something out front? Yeah, you can put it as the exponent. So this half is going to go up to that exponent. Okay, they will do that on the AP test on multiple choice, so that you got to get them to match up. So this actually turns into the natural log of 3. Because you might get here just fine, and then there's not that choice, and there's this choice. You have to be able to work your way to get there, okay? The next one here is tricky because people just don't recognize it. Does anyone recognize that? I'm going to move the 6 out, and I'm going to make that a 1. Does anyone recognize what 1 over 1 plus x squared is? Inverse tangent. Okay. A lot of people try to do like, oh, I'm going to try to move that to the numerator somehow, which you can't do because there's 2 pieces there. Or try a u substitution, but the x won't cancel. So the 6 just hangs out front, and then this just turns into inverse tangent. So you really have to be able to recognize those, or you won't be able to actually get an answer that's correct there. And then we're going from 1 to square root of 3. So I'm just going to plug them in first, and then we'll talk about them. So go ahead and do that. Okay, this one's a little bit easier than the front one. When you're talking inverse tangent, a lot of people just want to use their calculator. You won't always have your calculator for this type of problem. So if we're doing inverse tangent, that means the tangent of what gives me 1. So tangent is sine over cosine, right? So if we want to have sine over cosine be equal to 1, wouldn't they have to have the same value at that spot? So at what spot on the unit circle do they have the same value? Pi over 4. So our answer here is pi over 4 because that's what fills in that blank. Does that make sense? So really back here we've got minus 6 times pi over 4. And then up here we've got 6 times, and you're trying to think, this one's a lot more difficult, I think. You're trying to think the tangent of what is equal to square root of 3. So if I do sine over cosine, I'm getting square root of 3. So it's not going to be square root of 2 over 2, or the square root of 2 over 2 is pi over 4. The other options on the unit circle are 1/2 and square root of 3 over 2, right? So I just kind of stack them and see what happens. If this one's 1/2 and this one's square root of 3 over 2, couldn't you just multiply by the reciprocal? Is this what I was looking for here? No, because this is 1 over square root of 3. So if I flip them and I make the sine the square root of 3 over 2, and make the cosine 1/2, does that work? Yeah, that gives me the square root of 3. So when is the sine square root of 3 over 2 and the cosine 1/2? Pi over 3, right? We're talking about the cosine being 1/2 there. So that's what we're filling in this spot. It definitely requires a little bit of thought. So pi over 3. And then we can just clean it up here. So this turns into 2 pi minus 3/2 pi. So what is 2 pi minus 3/2 pi? Pi over 2, right? Or 1/2 a pi. Questions on that? You see it? Okay, this one you can do without to get some homework done. Tomorrow we'll have class for like the first 10 minutes, so we can finish that up, but you can really work on that homework. Is that on your page there? Okay, sounds good.